discuss Pushdown Automata, and it's called PDA. PDA is basically an automata, but it has memory as well, and this memory makes it more powerful. So with this automata, we can define more complex languages. So it has more power more than conventional automata. So using PDA, you can also define context-free languages. Those languages which are defined by context-free grammar can also be defined by Pushdown Automata. And for instance, you cannot define this language using regular expression or using simple FA, because here you need to remember the number of times A has occurred. So if A has occurred 9 times, B must also occur 9 times. So for this you need to remember that A had occurred 9 times. So for this memory purposes we need PDA. So let's move forward and see the terminology and symbols of this PDA. Before moving that, let's see this diagram. It says that languages defined by these tools, FAs, NFAs, and transition graph are these are languages. The PDAs, non-deterministic PDAs can define even more languages, including these ones, and non-deterministic PDAs can define even more languages, including these ones. So these are some symbols. For PDA, we assume that the input is coming from a tape. That tape has different cells, and the end of the string is shown by this null character, and it has these symbols. This oval is for start, oval for accept, reject. This diamond is for read a letter. This diamond is for popping, and these rectangles are pushing. So you have a stack where you can push, and you can push onto the stack, and you can remove from the stack. So let's draw a PDA for this simple FA. Here, because this is simple FA, so we do not need memory here, but let's try to draw a PDA here. We start with the start symbol, then you will see a read diamond, and here if you read A, if you read B, so this is basically for this state, starting state, you come back to this B. If you read A, you move forward, and if you read null, because string always ends at null, it means because this FA accepts any string with double A, because now until now double A has not been achieved. So for null we will go to reject state. And again for this state we have this read diamond, and on this state if you read B, you go back to the starting state. So for B you move here, and for A you move next, and again if at this stage you read null, again it will be rejected. And again here if you read A or B, you move back to the same stage. But if you read null, now because you have achieved your goal, double A, you have double A in your string, so now if you read null, it means the goal is achieved, you will accept it. So this is a simple PDA for this simple FA. Now let's see another example with memory. So this is a cleaner version of that. Here we have this input, and this shows the end of the input, and this is the PDA for this. So to understand this PDA, we have to, let's run this input on this PDA. We read A, we start from star symbol, this is the read symbol. So if you read A, you move in this direction, you push A onto a stack. So let's define a stack. A comes here, then you move back to the same stage. Again you read another A, push A onto a stack. A comes here. Because this language has same number of A's as B's, so we will push the A's onto a stack, and then for each B we will pop an A from the stack, so that when B's are equal to the A, then it will fulfill our requirement. For next A, again we'll push it onto the stack like this. Now we read B, and now we have a different path. If we read null at this time, so we will come here, and because stack is not empty, we will pop A or B, so it will be rejected. But as we see here, we have B, so we move to this direction, and now we expect that the pop must have A, because we have read a B, there must be an A onto a stack, so we pop. If it is not A, then it is rejected. If it is A, we move to the next state. So it was A, so we pop from the stack, and next we read another B, this one. Then we got another pop A from the stack, so we pop this one. So then we read another B, then again we pop another A from the stack. So now the stack is empty. Now we read null. So for null we move here, and now we try to pop the stack. The stack must be empty, and yes, it is empty. The pop returns null, so it is accepted. For any other scenario where B's are not equal to A's and not followed by A's, then it will be rejected. So you can try it yourself, draw it on the paper yourself, so that then you will definitely conceive the concept. Next we have another automata for odd palindrome. Here you know the palindrome is if you read from left to right or right to left, it will be the same string. So to understand this PDA, let's run this input on this, and let's assume that it is on a tape, and it is ending with null letter. Here we have these different letters. So first of all, we read this A, so we'll push it onto a stack. Let's define a stack here. Then we read another we read a B, we push the stack B on the stack. Then we read another B, again push on the stack. Now we read X, so we move into this direction, and now we read B. If we read B, the stack must return B. Yes, stack returned B. Then again we move to the read operation, and again we read another B. Stack must return pop B, tag pop B. And now we move to the read operation again. Now we read final A. The stack must pop A. Yes, stack popped A. Now we move to the read operation, and now we have this null operator. For null operator, we have this edge at this transition, and now we try to pop. It must return null. Yes, it will return null because it is empty, so it will be accepted. For any other path, you know, it will end up in rejection. So this is a simple PDF for odd palindrome. So this is a PDF for Even palindrome, here it is non-deterministic, so you need to be careful to understand where when the center is approaching. Like here, let's say we have a string a b a b a a b a. So this is palindrome, so it ends at null. So let's pass this on this period. We have to be careful that when we reach the middle of the string we need to change our direction. So let's see, we read a, push it onto the stack, then we read b, push it onto the stack, then again we read a, push it onto the stack. Now for next read, instead of moving to this direction, because it is non-deterministic, we need to be careful. Now we will move to this direction, and here when we read a, we must pop a. We read this a, so we pop a, so we popped this a. Next we have this read. Here we read b. For b we will pop b, yes, we will pop b. Next we have this a. For a again we will pop a, so we pop this final a. And now we have this null, and for null we will pop, because stack is empty, it will pop null, so it will be accepted. So now finally we see this example. This is a language defined, this is a conduct free grammar for mathematical expression, and we have to pass this expression on this PDA, and again it is non-deterministic, so we have to be careful while traversing this PDA so that we successfully parse this string. So let's define a stack. We start from here, we push S onto a stack, I push S onto a stack, then I come here, I pop, and now I pop S and I choose this direction because it will end up in successful parsing of the string. I pop S, so I pop S, then I push S again, then I push static, then I push S again, then I move back here and pop S. So I pop this S, then I push S again, then I push plus sign, then I push S. So now as you can see, we have almost achieved this string. So for now in next path I choose this path. Now I pop S. When I pop S, then I will read 4. So now the reading starts. I pop S and I read this 4. Then after this I come back here and pop plus signs. I pop this plus sign and I read plus sign, this plus sign, then come back again, I pop and I pop S, this one, and I read 4. So I read this 4, and then again I pop static. So when I pop static, I move this, I pop static and I read static, and then finally I pop S, this one, and I read 4, this one, so the string is accepted. Finally the string is accepted. That's it. Thanks for watching. Stay tuned for next video.